So this is how, this is about how semiconductors behave in an electric field. So now I would like to introduce another type of carrier conduction, which we call as diffusion. We have seen drift, which is essentially a result of electric fields which are applied to the semiconductor, and diffusion is basically a result of concentration gradients. For example, think of a semiconductor, which is in a hypothetical case here. You are having a semiconductor with some carriers, okay, and then some region of semiconductor is not having. It's an intrinsic region. Let's assume. Okay, it's going to have some few electron hole pairs, but just show intrinsic region adjacent to a region with a lot of holes. What would happen? Well, I mean, diffusion process, we are all familiar, how gases diffuse from high concentration region to low concentration region. The same thing happens even in the case of semiconductors. So this is schematically shown in the picture on the right. Okay. Before I do that, let me see. Okay, so you have additional holes here, right? So holes are going to diffuse here. So this is basically holes diffuse into the intrinsic region, right? Are electrons going to diffuse? Think about it. So we're talking about holes, right? Holes in the, in the left side you have holes, lot of holes here. They're going to diffuse. Is there going to be any electron diffusion? Well, it is going to be there. The reason is, remember, what is the concentration of holes here? Concentration of holes is going to be simply Na, 10 power 16. What is the concentration of electrons? Concentration of electrons is going to be N, which is going to be 10 power 4. I'll say that Ni square, I'll take it as 10 power 10. So 10 power 10 square is 10 power 20 divided by Na is going to be 10 power 16. So 10 power 4 approximately. I'm not doing the exact 1.5 into 10 power 10. I'm just taking Na is equal to 10 power 10. This is 10 power 10 I'm taking. Okay. What will be in this region? Here N will be P equal to 10 power 10. So you see that there is a higher concentration of holes in this region, so they're going to travel. Well, I mean, there's going to be a concentration gradient because higher concentration of electrons are going to be there here, and then it's going to come here. There is some subtlety involved here. It's not that simple. We'll have to go a little bit more detail. We will do that in the next lecture. Okay. All right. So what we're saying, concluding is essentially you're going to have hole diffusion, and you're going to also have electron diffusion. Electrons diffuse, okay, into, let's say, P region. Okay. So, I mean, essentially both, you saw that in the drift, we saw that both electrons and holes were contributing to drift current. Similarly, even in the diffusion, you have both electron and holes. So basically, majority and minority carriers both will contribute to current conduction, okay, in any case. And you could also understand it from, this picture here on the right, which is essentially showing you as a position of X, what is the electron concentration? Let's say the electron concentration is like this, okay? So there's a positive gradient to the electron concentration. You have higher number of electron concentrations on the right and the lower electrons on the left. So because of the diffusion, because of the concentration gradient, the electrons are going to flow in this direction, right? And by convention, whenever you have electrons traveling, we take it to be the current will be in the opposite direction. So we say that electron diffusion density is going to be in the positive X direction. Okay. Because electron flux is going to be in the negative X direction. So by convention, the current is going to be in the positive X direction. So this is for electrons. What happens to holes? Let's say you assume a similar concentration for holes as well. So you see this positive gradient. So hole flux is going to be in the opposite minus X direction. And the current density, because now it's positive charge, is going to be in the same direction. Remember this subtle difference. You saw that in the case of drift, the current density is always in the direction of electric field. Okay? Whether electron or hole, both current densities were in the same direction. Okay? But diffusion, the whole diffusion current is going to be in the negative direction relative to the concentration gradient. Okay? All right. So this can be written in a form of a current expression. So what we'll say is, let's write a let's say for electrons I'll write a diffusion current. I'll just J and diff I say. So essentially this diffusion current is going to be proportional to, of course, the charge, and then there is going to be a concentration gradient, and then there will be a diffusion coefficient. which is going to capture, whenever you talk of diffusion equation, right, you might have solved, or you will see it later. So essentially a second order differential equation space, you could solve it. And the coefficient of that is going to be the diffusion coefficient, which is going to be represented by dn. Diffusion coefficient times dn by dx. So what are the units of diffusion coefficient? Always, whenever you see equation, please take a little bit of time to analyze the units. That will help you clarify. And also, at any point of time, if you get confused, you can always verify it. So the current density is always going to be amperes per centimeter square, right? And this is going to be Coulomb, and this is going to be what? So dn, n is basically per centimeter cube, and then dx is going to be centimeter. So this is going to be 1 over centimeter cube, sorry, centimeter cube times centimeter, right? So d has to have, in the denominator, it has to have a second, because coulombs per second is going to give an ampere, right? And then on the left hand side you have centimeter square, on the right hand side you have centimeter power 4, so it has to be centimeter square. So the diffusion current has a units of, sorry, diffusion coefficient has a units of centimeter, sorry, this has gone weird. Yeah, so these are the units. Okay. And similarly, I could talk of a diffusion current for holes. So I'll say Jp diffusion is going to be the charge times diffusion coefficient for holes times dp by dx. Okay. And the same units for dp. Well, is the equation correct? Look at the gradient in the holes. The constant dp by dx is going to be the gradient in holes, right? This is dp by dx. And the current density has to be opposite the gradient. Okay, it's negative of that. So you have to put a negative sign for this. Okay, please do remember this. Okay, only for diffusion current for holes, it's going to be opposite, minus. All right. So, and then, okay, yeah, dn and dp are diffusion coefficients. We will tell you what these are. There are numbers you can calculate easily. Okay. All right. So this is a diffusion process, which is the second major process in a semiconductor device, semiconductor current carrying characteristics. Okay. So to sum it up, in a semiconductor you have two forms of current: the drift and the diffusion. Okay. So you have the drift component here. This is drift, and this is going to be a diffusion. So you have the electron contribution and the hole contribution. So you can sum up all of it and write it as this expression here. I mean, we just summed it up. Okay. So what it has is, this is for one dimension. Typically, we will only deal with one dimension. Two dimensions is very difficult to analytically solve. I mean, it's not going to give us any more insight. So most of the time, we'll use one-dimensional equations. But in general, if you have a full semiconductor, we have to use three-dimensional equations. In which case, you have to basically, these things become Ex, Ey, Ez. E becomes a vector, and then your concentration gradients become, sorry, concentration dn by dx becomes gradient of n and gradient of p. So it has to be a full three-dimensional solution, which can be done using computers. We do it routinely, but for this course, we don't need it. We'll most of the time focus on one-dimensional case. Okay. So what happens to a semiconductor which is in equilibrium? If equilibrium means the electron current is going to be zero and the hole current is going to be zero. The reason for that is that we already said that equilibrium means there is a balancing of Bria, right? So Jn equal to Jp equal to 0. So basically, the diffusion and the drift currents cancel each other, and you get zero current. So there is no net contribution of current from either electrons or holes. Okay. This has a very important implication for us. So let's see. So what does Jn equal to 0 mean? So if you look at the Jn expression, you have the drift current. For a moment, let's try to compute what is the carrier density. Okay, the carrier density, it will become clearer in in a short while why we are doing this. N equal to Ni exponential EF minus EI by KT, right? This is your carrier density. So what will be dN by dx? Dn by dx is going to be the same thing. The exponential derivative, if you take it, it will become the same thing. So N times 1 over KT, well, minus EI, right? So should be into minus DEI by dx. What is dEA by dx? You could try to rewrite it in form of electric field, right? So this we can write it as N times Q by KT. I'll put a minus outside. So this is going to be 1 over Q dEI by dx, which is simply electric field, right? So this is going to be minus N Q by KT times electric field. So now, if I say Jn, this implies Jn, this implies Jn equal to, well, okay, pardon my interchangeable use of Q and E, but you should be comfortable with that. So mu and E, and now diffusion current for holes is going to be plus E plus Q dN, and dN by dx is going to be minus N Q by KT times E. Okay, so your E cancels out, N cancels out, Q cancels out. So what you'll end up getting, and this is going to be equal to 0, right? So this will imply that equal to 0, so you can actually take the dN other side. So this will imply that dN by mu n is going to be KT by Q. Okay. You take dN other side and take the mu in the bottom, and then KT goes on the top. Yeah, this is correct. So essentially this is an important expression for us. So essentially what this is doing is it's giving a relation between mobility and the diffusion coefficient. This is called as Einstein's relationship. Okay. So we could also verify from the dimensionality. We know that D is going to be centimeters per second. Mu is going to be centimeters square per volt second. So if you do D by mu, you end up getting volts, right? KT by Q is going to be volts. So that's why this is valid. So you should remember this equation, because many times you are given mu but not given D. So you could immediately calculate KT by Q is going to be a point. Let's estimate. Let's take an example. Mu n is going to be, let's say, 18. Sorry, not 18. What was that? Mu n was 1450. In the last lecture, in the first slide, we had some number, right? 1350. Sorry. Yeah. Mu n is 1350 centimeters square per volt second. So what is dn? Dn is going to be 0.0259 into 1350. So whatever, it's going to be some number. Okay, it's going to be some 30, 45, some number like that. Okay, please check it out. Okay, and also remember, this can be a significant amount of current. It's not a small thing. Okay, the reason is You could take a piece of as an exercise. Take a semiconductor. Let's say take a semiconductor of size. Let's say 1 millimeter. Okay. Assume that there is a concentration here was 10 power 19, and here concentration is 10 power 18. So there's a gradient in concentration n. Okay. N is equal to 19 to, let's say, n equal to 18. And then you have dn, you calculate what is dn and compute what is the current. Okay. So compute Jn for this scenario. How much approximately? Okay. You will see that it's going to be some amps per centimeter square, tens of amps per centimeter square probably. Okay. It's a reasonably large amount of current that can flow in a semiconductor. All right. So diffusion current is going to be significant, and drift current also is going to be significant. We have to take both into account. All right. So